In this lecture, we're going to actually start down the typical route of organic chemistry and begin discussing functional groups one by one. We kind of go through the rest of the functional groups through the end of the semester. That really provides a nice way of kind of seeing the properties of organic molecules emerge. And so it's not so much just an organizational issue or an approach to organizing the topics, as it is actually quite convenient to build up and kind of build our skill set around some of the more fundamental and traditional functional groups that really aren't that practical these days to work with. But we learned some fundamental properties of things that we can carry forward as we look to the more relevant functional groups for all sorts of applications, which is kind of the hallmark of organic chemistry too. The first functional group we're going to get into is the alkanes, or are the alkanes, whatever. So the first functional group is going to be our alkanes. And you might say, Willoughby, we talked about alkanes already. Why are we continuing? And the answer is that it gives us a nice opportunity to start to discuss fundamental properties of molecules. But you're right, we have talked about alkanes already. We have actually said before, and I'll say it again, just in case it's not fresh in your mind, that alkanes have only C, H, and sigma bonds. So we only have carbon and hydrogen elements. We don't have anything else, and we only have sigma bonds. We only have single bonds. There's no opportunity for double bonding. If you do, you're outside of the scope of alkanes. And I think we've looked at this before, but just to remind us, if we had to say yes, no, whatever, is it an alkane? Here are 5 examples, and we would say yes, it's an alkane. If you look at the molecule, it's pentane. It's one of the fundamental alkanes, and it's just a straight chain, 5 carbons, 12 hydrogens, for 12 hydrogens, and no double bonds. The next molecule is benzene, so that's no. The reason why it's no isn't just because it's benzene, it's because it has double bonds. We can't have double bonds. Next molecule is ethanol. No, that has an oxygen. The last 2 molecules are yes. So we'll notice that branched hydrocarbons with only sigma bonds, like the last example, or cyclic hydrocarbons, like the second to last example, those also count. I mean, the carbon, hydrogen, only single bonds. That's what it takes. Okay. What we're going to start the next module with are chemical properties of alkanes in more detail. I'll give you a little preview now. It's not, it's not overly sort of dramatic as to what they do. The chemical properties and the chemical reactions are mostly relegated to combustion-like processes. So when I'm saying the chemical properties of a functional group, I'm talking about the reactions these molecules undergo and it's mostly combustion. And we've actually looked at combustion in quite a bit of detail. I mean, as much detail as we want to look at it in this class where we balanced chemical reactions and that sort of thing. So we're not going to talk about combustion anymore. In the next module, we'll talk about free radical halogenation. So that'll be certainly a topic for exam 5. Not something we're going to touch on today. So it's not so much the chemical reactions that I want to start with, it's the physical properties of alkanes, because again, this is us looking at some fundamentals of a fundamental functional group and trying to use those, the attributes that we can learn from this very kind of basic, I guess, functional group, not basic in the chemical sense, but I suppose in the derogatory sense, whatever. Just this kind of ordinary functional group, these trends can carry forward into more complicated molecules. So what I want to do is switch from chemical properties and talk about trends in physical properties. So what I want to start with is, and the trends are what you need to study. I mean, I realize that in the midst of COVID, everything's take home. So what you're memorizing is kind of your choice. But what I would expect in a typical semester, students to kind of commit to longer term memory are the trends, not so much the specific numbers. Now, what I want to show you is methane, which is CH4, right? Ethane, which is C2H6, propane, which is C3H8, and butane, which is C4H10. Now, what do I want to show you about each of these? I want to kind of compare their various boiling points. So the boiling point for methane is negative 161.7 degrees Celsius. Ethane, it's minus 88.6 degrees Celsius. Where is propane and butane? It's not in my notes. That's okay. I'm lecturing. I've got access. It's not in my notes, so we're going to use Google. So propane is minus 43.6 degrees Celsius, and butane is 30.2 degrees Celsius. Interesting. Oh, shoot. This is in Fahrenheit. So it turns out that we're pretty close to that equal barrier. So just Google gave me Fahrenheit at first. Let's correct that. Butane's a bit different. Butane is negative 1 degrees Celsius. Okay. So we have the boiling points for these first four hydrocarbons and first four alkanes. These are kind of these parent alkanes. They don't differ so much in overall structure, right? They're just straight chains for the most part, except methane was just by itself. Now, what I want you to take away from this is kind of the general increase in boiling point. We have something that starts off as very low boiling, which is methane. Now, if you look at ethane to propane, we see about little over a 40-degree jump when we go from a C2 to a C3 system. And then from propane to butane, adding another carbon is another 40-degree jump. Now, let's keep going. And I want to go from butane to hexane. So we're at roughly 0. But now let's go up to, I suppose we could go to pentane, which is C5, and hexane. Hexane, I've got 68.7 degrees Celsius. And then nonane, which is C9, has a boiling point of 150.8 degrees Celsius. Okay, now once again, very sorry. The professionalism is horrible here. I don't know why I didn't have pentane in here. So pentane is 36.1 degrees Celsius. So we go from -1 to 36. That's roughly another 40-degree jump. And then we go from 36 to roughly about 70. So it's closer to 35 this time. And then from nonane, we're adding 3 carbons and we're up to 150. So each carbon increases the boiling point by, I mean, if you think about what a boiling point is and how easy it is to measure some of these lower boiling things, it's not that easy. It's fairly interesting to see that a sort of pattern starts to emerge where it's close to about 30 to 40 degrees Celsius of an increase in boiling point when we have more carbon atoms. So the boiling point of alkanes increases by a sort of, well, it's not sort of, it's predictable enough. And whether it's 30 or 40 degrees Celsius. Okay, you think about there's going to be some error in certainly a trend like that for this type of pattern. Okay, so it's about 30 to 40 degrees Celsius per added carbon. So if you add carbons, you're going to increase the boiling point by 30 to 40 degrees. If you remove carbons, you're going to decrease that boiling point by 30 or 40 degrees. And notice it's not just carbons, there's also 2 hydrogens that come along for the ride. Now, why is this? That's a really good question. And in general, when you have more atoms, you have a higher boiling point. More atoms leads to a higher boiling point. And why is that? I mean, I guess that's just kind of restating what I just said. More atoms leads to more intermolecular attractive forces. Intermolecular attractive forces. Okay, so this is a really important concept, intermolecular attractive forces. First of all, when I write intermolecular, I don't know if you've had speech or oral communications, a class like that, where they talk about interpersonal versus intrapersonal, where intrapersonal is kind of the voice inside your head, and interpersonal is when you communicate with at least 2 or more people. Intermolecular means 2 or more molecules. And what we have is some sort of attractive interaction, something that's allowing 2 or more molecules to stick to each other. So these attractive forces, these make the molecules stick to each other. Now, it turns out that the intermolecular attractive forces, the things that allow 2 or more molecules to stick to each other, are the things that control the boiling point of a substance. So it's the, I'll rewrite it, intermolecular attractive forces control or dictate the boiling point of molecules. Okay, the boiling point is determined or dictated by these intermolecular attractive forces. Now, if you think about it and think about what these things are, it can make sense. So when we're boiling something, we're adding energy into the system, which is causing the molecules to move around, right? As we heat things up to boil or whatever, we're going to see an increase in the average kinetic energy of the system. So all the molecules are going to move faster. And as they move faster, they're going to kind of wiggle their way out and fire out of solution or out of the liquid state and into the gas state. Okay, if there's a greater attractive interaction between molecules, that is, molecule over here is more sticky to the molecule over here, we are going to see more of a tug as it tries to wiggle away into the gas phase. So these intermolecular attractive forces cause the molecules to stick more tightly into that condensed liquid phase and be less likely to escape. So it's almost single-handedly those attractive interactions between those molecules, between all of the molecules, that allows for things to boil at higher or lower temperatures. So what we're seeing is that more atoms leads to stronger intermolecular attractive interactions. Okay. Now, what we're going to do in the next lecture is we're going to look at the specific types of interactions. And so I think this is kind of a healthy way to kind of tie up the last bit of the modules, to change gears. And instead of focusing on something that's more technically advanced, we focus on some concepts, intermolecular attractive interactions. We're going to look at the various types of them in the next lecture, and then try to get to how to an explanation for how soap works, because it's all based on intermolecular attractive interactions. And it's actually a pretty fascinating lecture. I have a good time. Make a Fight Club reference. If you need a movie break, maybe I shouldn't recommend it, but I enjoyed it when I was your age. Okay, anyway, that'll do it for this lecture. See you next time.